Okay, what we'd like to do now is take what we know about our various ways of measuring enthalpy and entropy and put them together into a unified system we can use. So we're going to introduce this idea of Gibbs free energy. So remember the second law of thermodynamics and this definition of the change in entropy of the surroundings. So we said that the change in entropy of the universe is equal to the change in entropy of our system and that of the surroundings. And we were able to talk about the change in entropy of the surroundings based on this enthalpy of the system over T. So thinking about how the heat change, a reaction puts out heat and that heat is dispersed in the surroundings. Now, what we'd like to do is to substitute this in to our overall equation for the change in entropy of the universe. So now we have the change in entropy of the system and the change in enthalpy of the system. And now we have the universal change in entropy in terms of just the system. And this is great because it means we don't have to keep measuring the change in entropy of the surroundings. So we're going to multiply this through by negative t so that we can get rid of that t and that negative sign with our delta H. And so we'll do that negative t on the other side. And now we have this new equation that negative T, temperature in Kelvin, times the change in entropy of the universe is equal to negative T times the change in entropy of the system plus the change in enthalpy of the system. So we're going to define this new function delta G, the change in the free energy. And that's going to be negative T times the change in entropy of the universe. And now we have a new formulation. We have now delta G is equal to negative T delta S of the system plus delta H of the system. Or the way we most commonly write this is delta G equals delta H minus T delta S. So now we have this Gibbs free energy in terms of entirely system variables. And this is called the Gibbs free energy. We'll talk a little bit more about what it means to be free energy in just a moment. So this is a formulation of delta S of the universe in terms of system variables. And the cool thing is these are system variables that can be known. We can look up the change in entropy for molecules, right, in reactions. And we can also figure out the enthalpy of a reaction. We know how to do that. So we can find the Gibbs free energy of any reaction because we know these numbers. Now, just to review, in terms of delta S of the universe, remember we said if the entropy of the universe increases, then our process is spontaneous. And if it decreases, it's spontaneous in the opposite direction. It's non-spontaneous the way it's written. And if it's zero, it's equilibrium. But because we multiplied through by negative t, we have to switch our signs when we're talking about the Gibbs free energy. So in terms of delta G, if delta G is negative, then our process is spontaneous. And if it's positive, then it's spontaneous in the other direction, non-spontaneous as written. And if delta G equals zero, our system is at equilibrium. So let's go through a few examples of how we can use delta G and find it. So the first thing we want to know is we have iron reacting with water vapor to give us rust and hydrogen gas. And we want to know, is this reaction spontaneous at room temperature at 298 Kelvin? Basically, is delta G of this reaction less than zero, right? We're looking for a negative delta G. So we can look up the delta H reaction for this reaction and delta S. And please note, whenever you're doing Gibbs free energy calculations, delta H is almost universally given in kilojoules and delta S is almost universally given in joules. So you'll need to watch out for units. All right, so delta G is going to be equal to delta H minus T delta S. And we can plug in our numbers and we can do our unit conversion. And what we find is overall delta G reaction is negative 58 kilojoules per mole. Because this is a negative number, this reaction is spontaneous at this temperature. What about at 1,000 degrees Kelvin? So we can do all the same calculations, but now we have 1,000 Kelvin here instead of 298. Same unit conversion to kilojoules. And we're assuming here that delta H and delta S don't change a lot. That is a valid enough assumption for our purposes here, but they do change a little. So what we find is that this is a positive number, 41 kilojoules per mole. So this is not spontaneous at 1,000 Kelvin. It means a reverse reaction, hydrogen gas reacting with Fe2O3 to form iron and water, would be spontaneous. But as it's written, not spontaneous at 1,000. We can also say, well, at what temperature does this change its spontaneity? And in that case, we just need delta G equals 0. And in that case, T is equal to delta H over delta S. And we can just plug those numbers in, watching our units, and we get 709 Kelvin. So our reaction is spontaneous below 709 Kelvin because we know it's spontaneous at 298, and non-spontaneous above 709 Kelvin. We know it's non-spontaneous at 1,000. So we just found that point at which it switches. All right, so at what temperature does the spontaneity of the following reactions change? So we're going to look at tin plus oxygen and barium hydroxide plus ammonium nitrate and C5H12, which is a hydrocarbon plus oxygen to make CO2 and water. All of these, as you can see, have different delta H and delta S values, often with different signs. So here we have delta H and delta S both with negative signs for our tin plus oxygen, both with positive signs for our barium and ammonium nitrate. And then we have a negative and a positive here for our hydrocarbon plus oxygen. So this is going to help guide us in understanding our spontaneity. So to find the temperature here, we again are just going to do delta H over delta S. And we have two negative numbers. We get 2,790 Kelvin. Remember that a negative delta G is spontaneous. So, and delta G is equal to delta H minus T delta S. So one of the ways you can figure out if it's spontaneous or not above or below this temperature is you think about where it would be at 0 Kelvin, where the T delta S goes away. Since delta H here is negative, then it's going to be spontaneous at low temperatures. So in standard conditions, this reaction is spontaneous below 2,790 Kelvin and non-spontaneous above that. In this next reaction with barium, we again have delta H over delta S. These are both positive numbers. So we know that at low temperatures, since delta H is positive, this is going to be non-spontaneous. And only at high temperatures will we then have a spontaneous reaction. So this changes its spontaneity at 80.9, but it's spontaneous above 80.9 and non-spontaneous below because of that sign of delta H. If you're not sure what I mean, go back and double check, set T equal to 0 and see how delta H helps to do that. And then in this last one, we have delta H is negative and delta S is positive. Well, there's no such thing as a negative Kelvin. And because delta H is negative, we know this is spontaneous at low temperatures. Turns out this is spontaneous at all temperatures under standard conditions. There isn't a temperature where this becomes non-spontaneous. And that's because it's favored both by enthalpy and by entropy. Not only do we have an exothermic reaction that increases the entropy of the surroundings, but we have a positive delta S of the reaction. And so both the surroundings are increasing in entropy and the system is increasing in entropy. And so it's always spontaneous. So that's a good way to conceptually think about how to determine spontaneity by just looking at the signs of our delta H and delta S. So let's think about standard free energy change so far. To find our delta G naught, we need to determine delta H and delta S, but delta G is a state function, so there's another way. The standard free energy change, delta G naught of reaction, is the free energy change when reactants or products are in their standard states. And we can use a Hess's law like calculation again using delta G of formation. These are the standard free energies of formation, and that is what is the free energy change that you get from the formation of a mole of a substance in its standard state from elements in their standard states, just like we use delta H of formation. And like delta H of formation, delta G of formation is 0 for the most stable form of an element at standard state. So for example, oxygen gas has a delta G of formation of 0, just like delta H of formation. So now we have two different ways to calculate delta G. We can do it with delta G of formation, or we can do it with delta H and delta S. And delta G of formation, free energies of formation, are values in tables at the back of your textbook. So now that we've talked about how to calculate it, let's talk about what free energy really means. When we're talking about the Gibbs free energy of a reaction, we're talking about how much energy in this reaction is free to do work after we pay the heat tax. So this example in the middle of the slide is carbon in the form of graphite or like coal, plus hydrogen gas to give you methane. And the delta H of reaction here is negative 74.6. The delta S of reaction is negative 80.8, and that's in joules per Kelvin. So remember, we multiply that by temperature. Our delta G of reaction at room temperature is negative 50.5. That is the maximum amount of work that we can get out of this system, 50.5 kilojoules. And that is the entropy tax that we pay from our exothermic reaction, our 74.6 kilojoules that this reaction releases. The minimum heat lost to our surroundings is the difference between those two numbers. And that's the heat that goes into the entropy of the universe. So when we say that you can't have a perpetual motion machine, that is because we're constantly paying that heat tax. We're always losing heat to the surroundings. At the end of the day, we need to power our lives, our laptops, our cell phones, our homes, heat them and cool them. And we care about free energy because that's the energy we have available to do work. And we need to do work to do all these things. So that's why we care about the free energy of a reaction. And here is an example of where things can really add up. So when you want to heat your house, say with natural gas, you burn the natural gas and you pay a heat tax, you get some heat out. But when we heat our homes with electricity, we pay multiple heat taxes because every time we interconvert energy, we lose a little to this heat tax. So when we burn a fossil fuel to create energy, to make steam that we use to turn turbines, that we use to then generate electricity, which has to be transmitted, and then to come to your house and turn on your heater, we pay a heat tax at every single step, and it becomes less efficient. So this is why it's important to know about thermodynamics. So the other thing we should mention is that delta G of reaction is not the reaction rate. So we can determine if a reaction is spontaneous, but that's not going to tell us how fast it is. So here, for example, let's think about this reaction where we turn a diamond into carbon dioxide. This is carbon in the form of diamond plus oxygen to make CO2. It has a delta G of reaction of negative 397 kilojoules per mole. Delta G is negative, so under standard conditions, this is a spontaneous reaction. But we don't usually see diamonds spontaneously bursting into carbon dioxide gas, right? This is much, much less than zero. It's a very spontaneous reaction, but it's not a fast reaction. Diamonds are forever. This is an example that illustrates the difference between kinetic versus thermodynamic control. Thermodynamically, diamonds should change to graphite or to carbon dioxide, but the spontaneous change isn't observed because it's very slow. We say that diamond is kinetically stable with respect to graphite or with respect to reaction with oxygen, even though it's thermodynamically unstable. It turns out that diamond converting to graphite is in fact a thermodynamically favorable reaction. Delta G for that is negative 2.9 kilojoules per mole. So not only should our diamonds spontaneously react with oxygen, they should also spontaneously convert into graphite. But again, because it's thermodynamically favorable, does not mean it's kinetically fast. So now we can start to put together these ideas, right? The thermodynamics compares our starting point to our ending point. Kinetics is really the reaction pathway and involves our activation energy. So spontaneous is not fast. Thermodynamics just determines the equilibrium state of the system, right? It's where are we beginning to end? And it doesn't really tell us about what has to happen in the middle, right? This is thermodynamics. Delta G naught of a reaction measures reactants versus products. Kinetics determines the pathway. So is that barrier, that activation energy, very, very large or very, very small? That's the domain of kinetics. So because it's thermodynamically favorable doesn't mean it's fast. And that's why we usually, when we're really reporting a full picture of a reaction, we're talking about not only its thermodynamic values, but also its kinetic rate constants and activation energy.